Hi, welcome back to the breadboard. Today's video we have a 4-inch TFT display from Waveshare, and it's connected to a Raspberry Pi, and what I'm going to demonstrate is it running under Windows 10 for IoT with full touchscreen capability, replicating the screen here up onto the display. Now, to be fair, I've got a Windows 10 IoT screen, and I've done a screenshot of it and overlaid it on the Pi 4-inch TFT. It's a 480 by 320 screen, and I've then overlaid touch areas over the top of the buttons that are normally up on the screen up here. I've got calibration procedures for the touch screen that will actually save the calibration settings to the SD card so that the next time it powers up you don't have to do it again. It's got loading multiple different images, a little bit of a demo program that I'll run, and that's pretty much it. But anyway, the key thing here is that it is demonstrating the use of an LCD display, which will be very useful in IoT applications where you would want to have potentially a industrial control environment or heating and ventilation or something like that, where you have an LCD screen with touch-enabled input from the user, and you don't have the HDMI on here. Now, I've got the HDMI on just to make it more interesting and to show that you can actually have these programs written such that you can interact from either the LCD or the HDMI screen via a mouse, or both at the same time, which is the way this works right now. The principles that I'll show you in here will show you how to calibrate the touch screen, how to interact with its XY coordinates, etc., and well, basically run you through how it all works. The other part is talking to the Waveshare LCD screen. It's, like most of these LCD panels, it has a SPI interface on it, but in this case the SPI interface is not being used, even though you actually talk to the LCD board using SPI. And what Waveshare have done is they've put a couple of 8-bit shift registers along with a decimal counter, which will automatically do a load into the display via a 16-bit parallel interface every 16 SPI clock cycles. So it means that it's a little more convoluted than normal, and it threw me for a little while till I realized what they were doing, and I was able to fix the drivers. When you have a look at the software, you'll see what I've done there to compensate for that, and I've tried to comment as much as I can. Anyway, let's fire up the application and I'll show you what it does. So what I'm showing here to start with is both the Pi and the HDMI screen, just so that you can see them firing up together. I'm going to start the application now from the web interface of the Pi. So I've just clicked on start and it's going to load up. I haven't put a splash screen in there yet. So now you can see this is the basic screen. It's really simple. I've got your basic border here with number of controls: fill red, fill green, fill blue, calibrate, demo, an unallocated button, and the ability to quit the application. I've also got a number of smaller buttons down here, which is load image 1, 2, 3, 4, 5, 6, 7, 8. A little bit of a status screen on the main screen here, and there's a little button red round thing here, which is just for fun, which will actually track my XY cursor once it's calibrated on the touchpad up on the LCD screen. Now up on the main HDMI LCD screen, that is. Now on the Pi screen, let me just zoom in there so that you can see that one a little better. You'll see that I have exactly the same thing on here. Okay, so what I'm going to do initially is I'm going to do the button clicking on the Pi screen. I think I'll move you a little bit closer just so that you can see the effects square on instead of at a slight angle. Okay, so if I had started this and there was no calibration data stored in the SD card memory under the default user folder, then it would automatically go into a calibration. This is what it would look like. Right? So I click once, twice, and 3 times. And now that's got the calibration in. So now I can actually start doing things like fill red. All right, and as you can see, it's filling the red here. Fill green, fill blue, calibrate, which is actually going to take you back into the calibration again. I haven't finely tuned any of this, so it's not reflecting everything that I can do. The images, you can click on the screen, as I say, you can click on the LCD screen and do the same thing. I can click here and it'll load images up. So I have a few stored in here just to play with. And as you can see, it is reasonably responsive loading these images in. Okay, you can go back to fill red. So it's just working within this area. And the other thing I've done is I've written a demo which will just run through a few little demo application things with just vector drawing and stuff like that. I haven't got all the limits in here, that's why the odd occasion it's drawn outside of the box. It's basically trying to stay within the box as best as I can. Some of this line drawing is a little bit slow, and the reason for that is because the SPI interface is not blazingly fast with Windows 10 IoT yet. I am blasting it out at 50 megabits per second. The Microsoft Windows 10 for IoT outputs it in 16 byte chunks out on the SPI bus, and the interspacing between each byte chunk is a little bit slow, as well as between the chip selects. I do have a lot of optimization where I send 64K bytes at a time into the SPI interface, but it still chunks it into 16 byte chunks and has that little bit of a too much of a gap in between. Theoretically, you should be able to get a few frames a second refresh rate on the screen, but I'm not able to achieve that because of the drivers, but they will only get better over time. So anyway, that's basically the interface, and as I said, once I've calibrated it, there's a little ball on the screen, and what happens is when I'm running on the SPI on here, it's not moving on the LCD Pi screen, but it is moving on my HDMI screen in the foreground, just tracking the stylus as I'm touching it around the screen here. So what I'm going to do now is I'm just going to pull out a little bit from here and show you the big screen again so that you can track actually what's happening on it as well. Alright, so that's basically now both of them. As you can see there, that's now got the same display, and what I'm doing here is with the mouse I can actually go click these up here and you'll see that it'll do the same thing on both screens. So I got red and I got red, green, blue. The demo doesn't run on both screens, it's only running on the bottom one down here. The images I'm loading into both so that, you know, I'm showing how you can do that. Different images. Okay, so nice and easy. And the other part that I was saying though is that, you know, I can do this on here as well, and it'll actually interact with both screens. But if I take my stylus, and I can take my finger and do the same thing, but if I basically touch it and move it around, now you can see this little ball here, right here at the moment. It's actually tracking my mouse movements. So that's pretty cool. And I'm plotting in the status of this upper window here, the X and Y raw coordinates of the stylus, as well as the calibrated coordinates of screen pixels, and the pressure that I'm actually pushing with the stylus as well. It doesn't have a huge range because the pressure is actually measured between the X and Y coordinates anyway. But you can see there it just works just fine. It's reasonably responsive. I'm only sampling about 20 times a second for the XY stylus position on the touchpad. And as I say, it will work with your finger as well, see, quite happily. Red, green, blue, calibrate. Alright, so anyway, I think there's really not much else from an actual demo perspective to show you. I just, it's rather cool. Like I said, it's one of these Waveshare 480 by 320 4-inch TFT displays, full touch, resistive touch panel on top of it. It's got 2 shift registers on the back instead of using the SPI input directly to the screen controller, so that was a little bit of an issue that I had to resolve, but that's all done now. All the code is going to get posted along with the demo here, along with some screenshots and things like that. And I hope you find it useful. As I say, I'm trying to work on a set of libraries, and as you've seen over the last few weeks, I've put quite a few up there now for different devices. And the one thing I want to actually be able to do is create a user interface so that I can control my programmable power supply, electronic DC load, and various other power systems that I'm developing as a set of tutorials on my YouTube channel. And this is no exception to that. What I'm, as you can see, I'm slowly building up a set of tools, how to drive digital to analog converters, analog to digital converters, user interface screens, and things like that. And eventually I'll have enough tools together that we can actually build an actual product. And the very fact that I'm able to start this remotely using a web browser, have it interact on an HDMI screen as well as the TFT LCD screen all at the same time, I could probably actually have a web app as well that would represent this same screen without too much hassle either, but I haven't tried that yet. That will probably be another step that I'll do. I can also make this application start up automatically, and I've shown you how to do that on previous videos, where you can just set the app in the web UI to be started automatically, and it will just come up straight to the home page and start working without any issues. So I think there's pretty much, without going into a whole bunch of things that I've done on previous videos. Oh, one thing I didn't mention too, in the previous one where I did the Sharp 96 displays, these are the little black and white ones with, well, more of a silvery and white ones. They were being driven to a memory-based display buffer and then flushed out to the screen very, very rapidly by the SPI bus. But because they were 8 pixels per byte, and there was only 96 by 96, and 96 wide pixels is only 12 bytes, so it was only about a 1.5K of total buffer space. You can blast it out to the LCD screen very, very quickly. In this case, the whole screen, because it's 480 by 320, it's over 300K in size. So that takes a lot longer to send out, because it's 480 by 320 by 2 bytes per pixel, because it's 65K colors is the mode that I'm using it in. It doesn't go out very, very quickly. And so what I'm doing for things like the line drawing and even imaging on the smaller size of the screen here, right, this area here, is being sent directly from the image that's on the SD card. I'm mapping it directly pixel by pixel onto the screen, because it would be too slow to put it into a buffer, and the buffers would be huge as well. The opening screen, though, when I start the application, i.e. the whole backdrop, that is actually being written into a buffer and then sent to the screen as a whole image, just to show that you can do either way. But of course, because the Pi only has a gig of RAM, if you're using 300 odd K for the main screen buffer area, and then you've got workspace while you're loading other files and images and things like that to do the screen manipulation, it really wouldn't leave you much playroom for doing other data manipulation and your applications and stuff. So I've tried to minimize that by having some data sent directly to the screen. So any of the line pixel drawing, the font drawing, and things like that, as I say, if I run through the demo again, it'll so it's just drawing plotting squares, rectangles. Now it's doing line draws on here. Right, it's just simple XY line vector drawing. Now it's drawing arcs, and then it's going to continue with a purple circle, and then it's going to start doing text. Now this text is being driven from a font, and as you can see, you can write different colors, different sizes and everything, but it's all being based on an 8x5 font, and it's being scaled and written directly to the screen as I send the characters to the font character routine. I'm not writing it into a buffer, then flushing the buffer out, because that would just be too slow, at least from a user perception anyway. So anyway, the next thing is to have a look at the software. Might not do the video right away for the software. If there's enough inquiry for it, I will post all the software, so don't worry about that. You can have a look at it. If there's enough queries about how the software works and everything, then I will do a video to go through how it works. But I am planning on doing a more general video on programming the Windows 10 for IoT with these various SPI devices and things, and try and simplify and generalize a whole bunch of the functionality for you. But that's not part of this one. This one was about how do I get one of these SPI LCD screens up and running with full touch capability. This is using the 2046 Texas Instruments touch controller that you find on most of the LCD displays these days. I haven't tried any other ones. You will find when you look at the code too that there are drivers for a 320 by 240 screen in there, which was tested, but I accidentally broke my display when I was pulling it off of the Pi, so I wasn't able to show you that today, but it actually will work with the WaveShare 320 by 240 screen. And then the other one there was one based on the HX screen controller chip, but I haven't been able to test it because I don't have one. I did convert one of the libraries that I found for the Arduino on the internet. It took a complete rewrite. As I was having some difficulties getting this particular screen working, and I didn't know what controller it was using because it wasn't published anywhere about what the actual controller was. So I had to guess. So I tried an HX one. It didn't work, and then I finally, by examination of what chips were on the back of the LCD controller, I realized that it was actually using it in parallel mode, and there are slightly different initialization commands if you're doing parallel mode to the graphics screen versus using the SPI interface. And even though, like I said, this is using SPI, it's not using the graphics controller SPI interface. It's got a separate rudimentary shift register based SPI controller. So anyway, that's about all I'm going to say. Now I'm just going to finish it here before I start repeating myself, if I haven't already. If you like it, give me a thumbs up on YouTube. If you don't, well then don't. But either way, feel free to use the code as you feel fit. It's not production ready. There's a few, you can probably find a few areas where things could be optimized a little bit more, as well as maybe a bit extra error handling and bounds checking for the vector drawing and things like that. But basically it all functions as you've seen here, so enjoy. Okay, so we're just going to have a quick software walkthrough here. This is the main screen under Visual Studio 2015 for Windows 10 for IoT on the Community Edition of Windows Visual Studio. What we're looking at here is the actual GUI layout of the screen, which is very familiar because you've just been seeing it actually on the HDMI as well as the graphical screen. And what we have is a bunch of buttons on the left, which are delineated by basically a rectangular space here. And then we have these other second set of buttons, which are delineated by a second set of rectangular space divided evenly through the 8 buttons. So you've got 7 buttons here, large ones, and you've got 8 buttons here, smaller ones. Remember that because when we look at the code here now, we have a touch event handler. So I've gone through event handlers for buttons before, so I'm not going to go through each of these image click 1, 2, 3, 4, 5, 6, 7, 8 because they're basically what you've already seen on previous videos. So if you don't understand, go look at the previous videos for that. And if you don't understand event handling in general, then you're probably looking at the wrong video right now, and you probably need to go back to some basics and move on from there. Anyway, either way, the event handlers and also the touch handlers end up with the calling this image to screen, load image to screen routine, which will basically take an image that's been provided as a string, and it will load it and put it into a buffer, or to load it in and scale it and everything else, and then send it either to the screen and or the display. So this first one, await IL9488.load bitmap, will send it to the screen within this vector area, and it'll put it there directly on the screen. It won't put it via a bitmap buffer or anything like that. And then this extra bit of routine here will actually create a bitmap image and render it on the HDMI screen as well, because I wanted to reflect on the HDMI exactly what was happening on the physical LCD touchscreen. All of these are the event handlers for the buttons, and what we also have here, which is part of the touch screen, is this check action. And I'll go into the touch screen in a moment, but basically what happens here is when we come into check action, we have an XY coordinate of a finger slash pen slash touch screen event, where we detected that there was enough pressure to determine the fact that somebody was touching the LCD touch screen, and we wanted to figure out what we were doing. So the first thing we do here is we look at the Y coordinate, which is left and right, and determine that is it in the area that we are interested in for the left column, and if it is, we basically, then that's what this first thing does with the X is greater than 20, which is the up and down, and the Y is greater than 20 and less than 320, which is the other coordinate system. And if it is within that area, which is basically the upper left side of the screen, then it checks to see which button it was by doing a quick bit of math on the button, to basically dividing the area of that the buttons are evenly by 8, which actually gives you 7 buttons, because remember it's the top of each button. And if then it just does a case statement for each of the buttons, and depending on the area that it thinks you clicked in, it'll call different functions. And as you can see here, that the first few functions just are basically the same function call, just with a different parameter, either red image, green image, or blue image. And the you've got to do demo, you've got to do nothing, and then you've got an exit the application. And the other area, which is further inland on the screen, which is this area here, which is load image 1 through 8, what this one does is load different images which I've saved as part of the solution up onto the screen inside that display area on the upper right hand side of the screen. So what happens is, if you click on any of these buttons in this area here, it'll load that image up, and it knows the XY coordinates of this image as well as the width and the height, and it will just scale it appropriately and send it in there. That's what this load image to screen routine does. So continuing from that, what you've got is this demo function and the calibrate function. And what the demo does is it basically runs through a series of line draw routines, arc draw routines, and circle draw routines, and then finishes off with a few text-based font drawing routines, just to demonstrate a few other functionality that you can easily implement with the LCD display. And we went through the same thing with the Sharp 96 by 96 displays that were in one of the previous videos. One of the other things that I wanted to show you here, which were a little bit more specific to this, is if you is actually the touch handler. All right, so we're going to go into the tsc2046.cs file, which is actually all of the touch handling routines. And what we have here is two classes that are included in this file. One is the cal matrix, which I'll go into in a moment, and the other one is the TCS2046. The TCS2046 is the main class file that handles talking to the touchscreen controller. You've got the initialization, which sends out or sets up your X and Y coordinates, your SPI communication speeds, as well as your SPI chip select line, which is CS pin 0 in this case, I think, or CS1. And basically just, does the basic initialization of the SPI touch handler. You've got set orientation, which is just whether you're rotating the screen, landscape, portrait, upside down, left to right, etc. You've got a calibration routine here, which what this does is it takes a 3-point calculation for the SPI bus, and it takes a 3-point calculation from the touch screen and mathematically correlates that to the coordinate system for the LCD screen. So you've got a 12-bit resolution on the X and Y coordinates for the touch, and you've got a 480 by 320 resolution for the LCD screen. Now, obviously, when you start touching on the screen, you may get some parallax errors, which means that an XY coordinate for the LCD touchscreen doesn't exactly match the XY coordinates for the LCD screen. So what this little routine here does is compensate for that and gives you the best estimate that it can to compensate for any of those parallax errors when you did the calibration. Touch to display adjust is when you're asking for an XY screen coordinate, it takes the XY touch coordinate and uses the values that were correlated during the calibration procedure and figures out what the real XY screen coordinate is for you. I won't go into the maths because really I'm not a mathematical genius, and all I did was implement the algorithms. I really don't understand them fully, so I'm not going to try and pretend to explain them to you. Get display X, get display Y, all they do is they do the touch screen resolution to display adjustment, which we just looked at, and it correlates that to the actual XY and then applies whether you've got a 0, 90, 180, or 270 degree rotation on the screen for you. Display Y does the exact same thing. Get touch X and get touch X and get touch Y simply returns you the raw touchscreen values, which are the 12-bit resolution. Get pressure is a combination of the two, but basically here it's just a single parameter. And then the last thing is the check touch, which is called currently at 50 millisecond interval, so basically 20 times a second, to see if there is a touch on the screen sensor right now, the touch screen sensor, and if there is, then it will return you the XY coordinates of the touch sensing and the pressure. Now the pressure is determined basically by the X and Y coordinates and the value that you're reading on there. So it's fairly basic stuff, and so you just have a look at the code, and if you don't understand it, just post some questions and I'll see if I can answer it for you. And that's pretty much it for the touchscreen. It uses a standard TCS 2046 touch controller from Texas Instruments, which is basically a quad channel analog to digital converter, and it's using it in differential mode so that it can measure the X and the Y coordinates of the resistive touchscreen, and from that it can actually deduce where the XY point is that you're touching, as well as the pressure on the screen. There really is not much else to that than that. As I say, have a look at the code, and if you have any questions, just ask. And you know what I'm doing here is that when I actually check the screen to see if anything's touching, I just look for a pressure of greater than 5, and if I see it, then I assume that something is touching the screen and that it's a valid coordinate, and I'll read that coordinate, convert it to an X and Y screen coordinate as well, just in case somebody asks for it, and then I basically exit. So it's very efficient and quick routine that just scans, as I say, 20 times a second. The screen drivers, I've got this WS ILI 9488, and I've also got an ILI 948 without the WS in front of it. And the reason for that is because the ILS 9488 is where you are talking directly to the controller on the LCD screen using SPI, and there is no intermediate circuitry involved. The WS-IL 9488, on the other hand, these are screens, which is the wave share screens that are available off the internet, and most of the vendors like Adafruit, etc., sell the wave share one for the 4-inch 480 by 320 screens, and it uses a couple of shift registers with the SPI bus to take the SPI data and serialize it into parallel format and clock it into the LCD controller as RGB 16-bit parallel. So even though it appears to the Raspberry Pi as a SPI device, it's actually talking to the controller as a 16-bit parallel I/O device. So you have to make sure that when you initialize the registers, everything else, you do so appropriately, because as far as the screen controller is concerned, it's a parallel MCU that is communicating with it, not a SPI controller. And there's a few little nuances that are involved in doing that, which basically means padding a lot of leading high byte values with 00 just in order to get things to work properly. Anyway, what you've got here, so looking at what we have for the SPI graphics display device, is we've got this library in the WS-ILI 9488.cs, where we have the ILI 9488 display, which is a separate class from the main routines. It's not static, you have to instantiate it, which means that you can actually have more than one display device if you want to. And it has the XY coordinates, the data control pin, the reset pin, the current cursor XY coordinates, a buffer if you want to be able to do bitmap graphics before writing to the physical display, and then some initialization routines and things like that. Going down, then you've got a bunch of static routines, which allows you to initialize the display without instantiating any particular classes. You've got a whole bunch of variables which define the controls that are required to send to the display to do things. And then after that, you've got your a rectangle imaging structure, a GPI initialization routine, initialize the SPI display, which is your basic routine you've seen before. Obviously the parameters are slightly different, but basically it serves the same thing. It sets up the SPI device, it sets up the chip select pin for the SPI device, etc., etc. Reset display just sends out the standard reset display commands to the WS ILI 9488 display, which it's just a standard reset pin, set a command. Send the reset pin high, low, high, so that you actually physically clock the reset line on the display driver, and that's really all it does. You've got then initializer registers, which sends out a bunch of various commands that will initialize the SPI LI 9488 display. Now remember I said that this actually involves some padding because it's using a 16-bit shift register, where there's actually a decimal 16 or a decimal decoder where the 16th bit 124816, if you think about binary, is used as the clock line or the latch line for the LCD display. So every 16 SPI clock cycles, there will be a latch. So even if you're sending out an 8-bit command byte on the SPI bus, you still have to send 16 bits out on the SPI, otherwise it won't do anything for you. So what I've got here, as you can see, all of these, they've got a padding, and the padding is actually just a 00 value. It doesn't really matter what value you put there, but the point is that the command itself is in the lower 8 bits, and the ignore values is in the upper 8 bits for this. So every single one of these we've modified to have a padding bit to compensate for the fact that it's using this 16-bit shift register that is separate to the LCD display driver. Wake up basically turns on the display, nothing fancy there. The sleep does the opposite, shuts it down. Clean up, well, I haven't really done anything there, so you can ignore that. Landscape portrait mode just flips the horizontal vertical axes. Set address allows you to set a display range so that when you're sending data to these LCD displays, you define a work area on the LCD display. You can just stream data to it, and when you get to the end of the X coordinate, it automatically wraps to the next Y coordinate and resets the X. So if you want to do a block fill, you don't have to specify or manage rolling from the end of the X to the next Y line and then continuing. You just set the XY area of the LCD screen, and it will automatically roll around to the next line, the next line, the next line as you spew data out to it. So all you do is you set an XY, Y1, X1, Y1 coordinate, and XY2, Y2 coordinate, and then you just send a byte stream out to the display, and it will just take care of all of the wrapping and everything else for you. And that's what the set address range does. And I use that extensively for especially for character and rectangular drawing onto the screen. RGB 24 to 565. That's just a standard function that you give it a 24-bit RGB, which is 888 RGB bit signal, and it converts it to the RGB 565 format. So it's nothing fancy there. Used for all the other routines. Initialize display buffer basically just rips through the, in this case, 480 by 320 screen and initialize it to whatever color you tell it to use. And then it will, it doesn't automatically send it to the physical screen. You have to do a flush buffer in order to get it out from beyond that. Load bitmap will take a file name and it will load it into the display buffer. It won't write it to the screen for this particular one. It'll load it into the memory buffer, then allow you to flush the memory buffer to the screen physical display. The next one, though, which is also an override on the load bitmap, where you specify x1, y1 width and height, and then a file name. This one will actually output the file or load the file into memory, scale it, and output it directly to the display. Flush will actually take the first one of these two load bitmap kind of functions, or if you'd be doing any drawing or writing stuff into the display buffer, then this routine will actually block it out to the physical display for you. It's a fairly similar and functional capability to the one that was done for the Sharp x86 display routines. Send command and send data, these are just basically fairly simple routines. Send data will take a byte array and send it up to the maximum that the SPI bus allows, which is 65K, out in chunks out to this whatever device you happen to specify. The send command basically does the same thing, but it uses a GPIO data command pin. It's set to the low value and it does the same thing. Now this one doesn't do any chunking because none of the commands for this particular display require more than a few bytes at a time, so there's no point in chunking it because you can send whatever happens to be required in one go anyway, so without an issue. Pixel draw, line draw, horizontal, and line draw vertical. These are all very specific to the physical hardware and have been optimized for it. So that's why when you look at these, you've got send command and send data built into them. They're not dependent on anything else. They're actually directly communicating with the hardware. I won't go into any of the nuances of that, but you can see these are very similar to the ones that we've talked about in previous videos. So this one here, which is the fill rectangle, it also is a very specific to the hardware. So I'm just going to move that up and put it in the right place, just because it shouldn't be down in the generic routines. And in the generic routines, you've got draw line, arcs, arc extended, draw circle, draw character, write a character string, write a character single character, and draw a character to the LCD screen. Or actually, it doesn't. In these cases, it doesn't actually care what it is. What these routines down here, they're very generic, and what they do is they actually rely on things like draw horizontal, draw vertical line, or if you go down here, you'll see that it actually ends up calling the draw pixel. All right, so these don't actually know what the physical display looks like. They're very generic, and what I'm going to do eventually is separate these into a separate library so that they don't care, and they'll just inherit from whatever the physical hardware library is and make it more generic. Obviously, things like draw character, set cursor, draw character, write and write string, they also basically end up ultimately calling either the rectangle function or the draw pixel function. So I'm not going to go into that either in any detail because I've done so in previous videos. And if you have any questions, just post it and I will happily try to answer any questions on that. And anyway, that basically gives you a rundown on the graphics library for the WaveShare 4-inch 320 by 480 or 480 by 320, depends on which way you look at it, graphics driver, LCD panel, and this will also work with the ILI 9341. Now I did actually get the drivers all working for the IL 9341, but I broke my display, which was most unfortunate. When I was taking it off of the Raspberry Pi, I actually ended up somehow managing to crack it, which means it basically doesn't work anymore. So I'm unable to show you it in the previous video sections of it working, but it was actually working. So fortunately, I had a second one, which is the 4-inch display driver, and once I figured out what the actual chip was, I was able to get this library up and working. The HS HX8357.cs. I haven't tested this. There's no reason to think why there should be anything fundamentally wrong with it because the initialization routines are all correct and everything else. I just haven't been able to test it to see whether it works properly. But it was converted from an Arduino library that I found, and I've converted it fully to the C# libraries as well. And then you've got the two fonts, and the one I'm using currently in the demo is the font 6, which is an 8-pixel vertical and 6-pixel wide font. I haven't yet written an abstracted character driver that will take any font. So I've got a font 12 here that's actually currently sitting in the solution, but I'm not using it yet. If you get an inclination to write the driver to or adapt the driver to use it, then great. Please feel free to do that and then share it with the community. The main routines I think we've already covered here, and everything else I think pretty much is the same as previous videos. So I'm not going to talk about how to get this thing deployed to the Raspberry Pi or how to use the XACML
or sorry, XAML, as somebody pointed out, it should be pronounced, display functionality working. It's all that's really irrelevant, compared to showing you how the drivers work. But anyway, I hope if you like it, you give me a thumbs up, and if you don't, well then don't. But you can take these drivers and use them as you will. They're not production ready. Some of them don't, as you've already seen when you run the demo. They don't actually do all of the bounds checking or the error handling that you would want in a production solution, but they are all functional. And what that means is that basically you don't have to invent anything. You just have to make them a little more robust if you want to use them for anything production wise, by adding a little bit of extra error handling, a little bit of extra bounds checking, and things like that. Um, I think the most important takeaways from this is that at the end of the day, writing to the SPI devices and things like that, if you've been following my videos, is following a fairly consistent theme. Once you've instantiated the SPI drivers and everything else, it's just about sending byte arrays to the right thing with the right chip selects and stuff like that. And that's pretty much it. And everything else apart from that is what are the right commands and data sets that you need to spew out to the physical device. And once you've got beyond this SPI driver, you really don't care about how that works. You can basically forget about it and just focus on sending the commands to the devices, which makes life much, much easier. And that's what I'm trying to get to. And I think in a future video, not too far away, what I'll do is I'll ignore the hardware that we've been talking about, for instance, in this one with the 9488 display driver, and actually focus more on how the SPI bus and chip selects and everything else works, and just talk generically about the hardware. Because really, once you figured out one, you can basically just have a set of basic functionality that deals with it, and then forget about it, and you just focus on the higher level functionality of the chip that you're trying to talk to and the functionality that you're trying to do. And what I want to do with this thing is have some functionality that allows me to build a electronic computer controlled Raspberry Pi, maybe focused power supply, multiple channels, etc., with isolation circuitry, and be able to control it, monitor it, and have a touchscreen interface that allows me to do this complete industrial control kind of environment and have it web enabled and everything else, but without really having to worry too much about what the physical hardware is doing. And by having a set of libraries that are written, and I've been slowly building on those, because you've already seen the fact that I've done the analog to digital conversion, digital to analog conversion, I've done LCD, Sharp 96 displays, and now with the touchscreen controller, as well as a high resolution 480 by 320 64K color LCD panel. There really isn't much left except focusing on an actual application. So what I think I will probably do next on my next video is, well, actually put all of these different videos together into one master application and see if we can start with here's a power supply. It's touchscreen enabled, and you can set your voltages, you can monitor your current, and you can monitor your power. You can do data logging and all sorts of fun stuff, all based on all of the previous videos that we've done up to now. But anyway, for now, as I say, I've basically the libraries following a consistent theme. I haven't optimized them all and made them all consistent yet. I'll probably do that before the next video, so that you can pick which screen you have, which touch panel you have, and various other things. Use a consistent set of libraries and stuff like that, and go on from there. Now, before I leave, though, one thing I wanted to mention is that with this, when you saw earlier in the video, I was able to run a calibration procedure. And what I did with the touch panel, I need to open it up again, is I wrote a routine that actually allows me to save the touch calibration settings. And what they're built into is this calibration matrix. I mentioned that I was going to talk about that before. So in the calibration matrix, this is all driven by a set of available routines that the algorithms are available off the internet, the Google. I will post the relevant links when I do the posting. I can't remember off the top of my head right now while I'm recording this video, but it's not new. It's been around for quite a long time, and Adafruit and Atmel and a whole bunch of other manufacturers have used these same basic algorithms that have been around for probably over 20 years to do the touchscreen calibration and 3-point. That's all you need is 3 points of a touchscreen correlated to the physical LCD display to be able to accurately or fairly accurately estimate where somebody is actually touching on them and give you a good representation of a control mechanism through touch on that screen. And so what I've done is I've implemented the same routines. I looked at what Adafruit had done and Atmel had done and basically adapted it for use with C# and the TCS 2046 from Texas Instruments. And what you see is basically the result of that. But it's nothing new, as I say. The reason why I don't have credit to Adafruit or Atmel or anything like that for the touchscreen stuff is because they basically didn't invent it. They created their own versions of the algorithms, and I've done the same. I've used a little bit of hints from their ones, which gives them credit. They did a good job with it. But I've adapted it for C# and I've tweaked it a little bit, and I've added routines to actually save the data to the SD drive that you have plugged into your Raspberry Pi. Now, I'm going to spend a little bit of time right now just to describe this very quickly. In that you've got this save calibration data. So ignoring the actual calibration routine, what we have is a parameter, a bunch of integers, A, B, C, D, E, F, and div. The div is a master divider, and then I've got a message, which just allows me to feed back to the main UI what happened when I tried to save or load or whatever from this thing. If the div is 0, then I basically am assuming that there is no calibration data available, either because it loaded and it was bad data or because it's never been created in the first place. If the div is anything other than 0, then I assume that everything else is good, and we'll go with that. But what I've done is the Raspberry Pi under Windows 10 IoT, it's not easy to save data to the physical SD card. You have to set permissions by going into the actual application, and I'm doing this right now while I'm recording here so that you can see. If I just go properties and I go to assembly, no, not assembly information, manifest. Yeah, and then capabilities. All right, what you've got is these things like internet client, music library, picture library, video library, removable storage. And one of the things that's missing here, which has been deliberately done by Microsoft, is the default documents folder. Now, I don't know why they took it away, but they did. And if you actually just, instead of opening the file via the graphical interface, if you go in and you open the manifest here by looking at the code instead, you'll see down here that what I've done is I've manually added this one. You can't do it through the GUI interface, but you can do it manually, which is Documents Library. And if you do this, then you can actually start now writing and reading from the Documents Library folder and be able to save your calibration data or any other data that you really like if you want. And the other part of this is you actually have to specify the file type that you also want to be reading from. So what I've done here is I've given it a suffix of .cal for the calibration data. And the way you can do that, you can do it directly by typing in here, or you can just go to the project solution and say properties, go to manifest and capabilities. No, not capabilities, declarations. Yeah, declarations, and then file type associations. And what I did was I added one, and I've said that my file type is .cal. I mean, this content type is just basically text crap that you need. But if you do this kind of declaration, then what you're able to do is you'll enable your application to load that type of file from the physical hardware, in this case the SD card. If you don't do one of these, then it'll give you an access denied. All right, so any file type that you want to load, you have to declare it ahead of time to be able to do it. And you do that with available decorations. You just click add, and you can select existing ones, or you can just click and then you just click add, and it'll put it in here, and then you can start specifying your file types and things like that. So in my case, I've added the .cal, which is the extension I gave for the file. All right. Now the next thing that you have to do for that is you have to start creating the basic variables. So here's a couple of routines. One is the save calibration data, and one is the load calibration data. So for the save calibration data, what we do is we create a save. So we take the string array of lines, and we take all of our different A, B, C, D, E, F, G, and div, and we create an array of strings for it by just doing dot to string for all of them. And then we create a folder object, which is to the documents library, and we create a file where the file name, and then we obviously modify the file extension to .cal no matter what the user decides they want to put in, and then we create the file and we overwrite the file name if it already exists. Where we don't really care in this particular case. You can add code obviously to handle adding a date time format and various other fancy stuff. But right now, for the sake of the demonstration, I just said, you know what, I'm just going to use whatever the file name is, and if it exists already, I'm just going to override it, and that's it. So it's pretty straightforward. And in the object for the class library that I've got for the calibration points, I've got a message folder where I can actually provide information back to the calling routine to say what the heck happened when I tried to save or load and things like that, which is this. What this did is in some of my earlier videos, I started trying to pass a screen-based status text box, and really at the end of the day, if you don't have a screen-based status text box and you want to be able to do things, it really isn't the way to do it. So what I did was I provided a string field in the object that I'm creating where I can put some messages, and if it worked fine, then great. And the other bit that goes along with that in this particular case is a date time field where I've got the last updated. So when I successfully save it to the screen with valid calibration data, this last updated date is the date time of when I save that data. If I have an error with it, what I do is I do datetime.max, which is basically 2099.99 or something crazy, 100, 200, 1,000 years in the future or something, so that it's easily identifiable as being an invalid date time for the current calibration data. And then for the load routine, what I do is I go for the same file name, whatever file name it is, ending with .cal. I load it in asynchronously, and then I basically split the line using a comma, because it's basically a CSV single line file, and I then just assign the byte array to each of these different things by using the convert to ints. And if there is an error in the div, so basically if div is 0, then I give an error message. Otherwise it's it says it's good data or bad data. And everywhere else I look for basically saying if div is 0, then I don't assume that the calibration has been done yet. And that's pretty much it. And if I catch, if there's an exception load in this routine, then I set as I said, I set the last dated update to the datetime.max value, and I set everything else to 0. And if I've got an exception thrown, because I've ended up in here, there's obviously been an exception thrown, then the message response is filled with the exception message so that I can put it in anything I like. Which in this case, if you look at the main page.aml.cs, you'll see that the message field is put into the status field, so I can see whether I got an access denied, file not found, or whatever it might have been. And that's pretty much it. So, the basic thing that you can see here is that I've got touchscreen, I've got saving to a physical file on the SD card. I can read from it, so that as long as the SD card has that file available, then it's not going to write to the SD card every single time, and so you've not got issues with wearing out the SD card or anything. But it'll load it, and then it'll allow you to have accurate XY coordinate system for your touchscreen. And you can go from there, but you can obviously call the calibration routine anytime you like to reinitialize it if you want to. And that's pretty much it. So between this and the ILI 9488 .cs file, you've got complete 480 by 320 65K color graphics to screen with full touch screen capability as well. On top of that, with event handling, via the HDMI screen, all linked together, and now you've just in a position where basically do what you need to do, because you've got all of the tools that you need here available to write your own application and make it as complex or as simple as you want and do your own thing. I've just provided you the tools to do the job. You don't have to think about too much about how to make all these things work, because I've done that for you, and go for it. Your limitation is your own imagination. So if you like this, as I said, give it a thumbs up. If you don't, then don't, or whatever the equivalent is on Hackster / Element 14 / YouTube, whatever. If you like what I provided to you, then give me some credit for it and provide me a thumbs up, or kudos, whatever it might be, respect, I think it is on Hackster, etc. Anyway, that's it. So provide me feedback, provide me questions, whatever you like. But either way, use it as you feel fit, and I hope you find it useful and can make something good out of it.